Thank you, and thank you for making time here to attend my presentation. We're going to go and cover pretty much the work that appeared in my dissertation in the presentation today. And I'm thinking about how we manage power with some hard upper limit to how much energy our system can draw. All right, so a little bit on my background. Got my undergraduate degree at University of Oregon back in 2004. At the time I was interested in computer networks and distributed computing. Then I had my sojourn in industry for a while where I worked in this big data space. How do we go and bring in this data and respond to it in real time? And this then set me up when I went back for my PhD to work in this power management space where we're doing power management across the machine instead of power management within a particular device. Because that has this real-time flavor where I need to get intelligence across the entire machine for consumption, make a decision, and then apply that decision across the computer. All right, so we'll talk a little bit about energy efficiency in HPC, since that is a little more studied than the power problem. I'm also going to try and talk about how the energy efficiency problem is different than the power problem. Then we'll talk a little bit about hardware overprovisioning research and power scheduling, as well as how power capping affects application performance on our machines. Then we'll talk about the PowerSched algorithm, and if there's time, we'll talk about a simulation model that I have that helps to study the way that power scheduling behaves across one of these large clusters. All right, so of course, when we think about our HPC machine, we can think of a user interaction model that looks like this. The user is there at their terminal. They have some application that they want to run, and that gets sent to the job scheduler. The job scheduler is then responsible for managing the resources inside of the HPC system. Generally, this is done at the level of nodes. When sufficient resources are available, a job gets scheduled on those nodes, and after the job completes, that output comes back to the HPC user. And this is the traditional way that we interact with and timeshare these large HPC machines, and the traditional way that we manage the resources. So when that job comes in, it comes in with a resource profile that needs to be matched for the job to run. Okay, those of you that were doing HPC work 3 years ago, this was the table that ended up in every presentation talking about the exascale targets from the Department of Energy. And the thing that we were all scared about, or that most people got scared about, was the power requirement, right? We're going to go and increase most of the other capabilities of our machine by 2 or 3 orders of magnitude, but we only get about 3 times the power budget, a single order of magnitude there for power for this new machine. All right, and this gives us a notion of what is the energy target that we need to hit per floating point operation. We have a machine that we want to have do an exaflop worth of computation. We want to do that on about 20 megawatts worth of power, and that means we need to get each one of our floating point computations down to about 2 picojoules. This also fits with that flops per watt metric that shows up in green computing, because that's really a measure of energy rather than a measure of power. So typically we think about energy in terms of power times time. There are several mechanisms we can use to control the energy within our system. We can get energy efficiency by using more efficient hardware. We can do that by reducing the size or changing the materials. Dynamic power gating is frequently used inside of our hardware. That's where we turn off circuits within the chip that aren't being used for the current set of computations. Dynamic voltage and frequency scaling is where we adjust the clock speed on the processor. And when we adjust the clock speed down, we can reduce the voltage that we drive that processor at, and that allows us to get power savings on the processor. And as long as we don't extend the runtime of our computation using DVFS, we can get an energy efficiency out of that. RAPL is an interesting technology. It doesn't necessarily give us energy efficiency, but it does let us set a power target, and if that power target doesn't change our runtime, then we still get an energy savings. We can also think about acceleration technologies, like GPUs and FPGAs, where we go and more efficiently organize those computations on our chips. And the last thing that we see are changes to the source code. If I change the number of threads that I have execute, that changes the mapping of threads to hardware execution units. And if I plan things out correctly, I can see an energy savings potentially using that indirect method of power control, whereas these other methods deal directly with the hardware and the way that the energy moves through the hardware. Okay, so lots of HPC energy research. This is just a quick smattering of some authors that have done some work recently. And I have them grouped based on whether they are changing the power consumption without increasing the runtime significantly, or if they significantly reduce the runtime. If we significantly reduce the runtime, it's possible and probably likely that we will increase the power usage when we actually execute the program. Okay, so when we build an energy efficient supercomputer, we end up introducing another problem for the power. So I'm going to use less energy total to do the same computation, but I'm going to get inconsistent power consumption across the machine. So we have a plot here from a paper from Patke in 2013. This is for Vulkan, which is one of the machines at Lawrence Livermore, over several months. And we can see the burn-in phase when they run LinPack on the machine, and it uses almost as much power as has been budgeted for the machine. It draws 2.3 megawatts of the 2.4 megawatt power provisioning that's been done for the system. After they finish running LinPack on it to get their top 500 score, they run their real science on the system, and we see it bop along at about 1.5 megawatts worth of power. So a couple of things we can think about with that is our power costs around $1 million per megawatt. So someone who's doing accounting is going to say, well, are we wasting $1 million a year on energy that we're not using? Right, another way to look at this is, you know, there's 30% of the power unused. If I had 30% more nodes, could I do 30% more science on this machine? So could we go and get some additional efficiencies here for the work that we care about if we had some more hardware in the system? If we added more hardware, then we have to be careful because someone could run LinPack on the machine again and exceed our power cap. And if they exceed it by enough, that causes a problem for the electrical infrastructure that we're plugged into. And that leads to an idea of hardware over provisioning. So we want to go, this is an idea for the HPC community that was proposed by Roundtree in one of his papers. And the goal is to productively use all the power that we've budgeted. And ideally, we'll be able to use that power in a way that will allow the machine to make good progress on all the jobs that are concurrently scheduled on the system. The high-level strategy is to go and add more nodes. But as I mentioned, if we go and add more nodes, then we've introduced another power safety risk or power risk issue with our system. So I'd like to pause for just a moment and tease out that energy isn't really power times time in the way that we think about it. It's an integral, and it's important to keep that in mind because our computation may have different phases associated with it. We have a high compute phase where we're doing a lot of processing, and then maybe we have a low compute phase where we're doing a bunch of I/O. And so we don't have a simple power characteristic to our applications where I can say that this application draws this much power over its entire runtime. We have to be more careful to understand that this application draws this much power at this time, and at some other time, that power consumption may be different. Of course, when we look at it in this way, we can think of the application's power consumption there as a function, and the energy that's used for the computation is the area under that curve. Okay, ideally, if we run several different jobs on our hardware over provision system, we'll get power consumption that might look like this plot, where I have the gold job that's in a high power consumption phase, while the green job is in a low power consumption phase. And then when the gold job goes to a low power consumption phase, the green job goes to a high power consumption phase. That allows both applications to get all of the energy that they need and to run at their maximum execution rate on the machine, while maintaining some power cap that is less than what the average power of these two applications are, what the maximum power draw is for these two applications. Another plot that I like is this one here. And this one highlights that a power cap is different than an energy optimization problem. We have the same application. It's been implemented as a GPU-based application and a CPU-based application. This trace is from Titan. And if I think of having a 7 megawatt power cap, it doesn't matter that I have a more energy efficient way to run this code. If I'm capped at 7 megawatts, I can't use the GPU code because that will exceed the power cap. And then, of course, that's more a problem if the power cap is a hard power cap based on some electrical infrastructure reason than a soft power cap that may have been put in administratively. At the time I started my work, we didn't really have any power scheduling research to speak of in the literature. The easy thing to do if you had one of these systems where you couldn't run it at its full power consumption was just to set the same fraction of the power to all of the components and run the system that way. So that's the naive scheduling strategy that most of my work compares against. When I think about power scheduling, I think about two different parameters that we'd like to pay attention to. Think about the level of power limit enforcement. Is it important that I maintain that maximum cap? If it is, then I want to be in this hard enforcement space. If it's okay for me to exceed that power cap from time to time, then I think of it as a soft enforcement space. I want to optimize for that power target as best I can, but if I miss it, that's not a big deal. Another thing that I think about is when we make these power scheduling decisions. So for the naive strategy, it's a static scheduling strategy. We set the power once when we turn the machine on, and we never touch those power settings again. Another strategy is what I refer to as the reservation-based strategy, and this is the way that we typically provision our resources inside of the HPC machine. At the time that I submit my job, the job scheduler makes a resource reservation against the computer and then schedules my job on those reserved resources. So I say I need 5 nodes, I get 5 nodes from the machine. In the same way, I might say I need 100 watts per process that I'm running, and the reservation system would go and reserve those 100 watts of power for the duration that my execution or that my program is executing. The last scheduling time bin that I think about is the dynamic scheduling, and this is where we can go and remake the scheduling decision at any time during execution. So after the jobs have been placed on the resources and begun execution, it is valid and can be done to change what that power setting is for that particular CPU or for that particular job that's running. So, we can also think about this in terms of going from more static scheduling to more dynamic scheduling, with reservation being sort of a middle ground where I make the choice dynamically as the job start, but not dynamically during the job execution. Okay, for hard enforcement, we want to go and formalize that, and I propose a power scheduling invariant to handle that formalization. At all times, we want the system power limit L to be greater than or equal to the allocations that are made across the machine. So for every component I at whatever time step we're at, we want to make sure that the aggregate allocations are beneath that global power limit. And then, of course, the allocation should always be greater than the actual consumption on the machine. And that lets us break down proof for hard enforcement into 2 pieces. We have the algorithmic piece, where we need to prove that the algorithm we use to make allocations guarantees that the aggregate allocations never exceed the total system power limit. And then we can go and look at the mechanism component. Do we have something that guarantees after I've set an allocation that that allocation cannot be exceeded? So those are the two pieces that I think about, and when we go over PowerSched, we'll talk about how these are satisfied by that solution. Power scheduling research has grown a lot since I started. Several different schedulers have been suggested. Many of them are in this reservation space where we go and treat power like another typical HPC resource. And when we start the job, we come in with a power estimate. Most of the work, and I haven't listed most of the work is in this soft enforcement space where we use modeling of our applications or other hints to try and guess what the power consumption of our application is going to be before we launch it on the system. And this, of course, is a challenge for hard enforcement. Due to the halting problem, we can't know what your execution is actually going to look like, and that makes it hard to make a hard estimate on what your power consumption is actually going to be when we place you on the machine. Yeah, so this is more of the same, talking about the way in which we model applications. One of the things to note is that several of these works use average power as the estimation. So when I generate my application trace, to make my estimate from, I compute how much energy was used by that run and divide that by the runtime. So is average power a good metric to understand and estimate our application's power behavior? Also is a question that hasn't been fully explored, I think, by the community. Okay, so I'll talk a little bit about power capping effects because I'm going to be using RAPL's power capping mechanism for my power scheduling strategy. Lots of work focuses on DVFS. DVFS has been available to researchers longer than RAPL-style power capping. DVFS also has a really nice behavior with respect to estimating what your program execution is going to be. With DVFS, we set the clock speed, and how much we reduce the clock speed gives us a nice ratio that we can use to estimate what the new application runtime is going to be on our system. RAPL doesn't have that property associated with it. When I set a power target on my processor, it may change my application runtime, or it may not change my application runtime. And as we'll see in a later slide, the impact that setting that lower cap has is nonlinear. So if I cut the power in half, that changes my estimated runtime by more than half for my application. So here are a couple of benchmarks that have been run at progressively lower power caps. There at the right is 115 watts, which is the maximum power setting for the processor that these were run on. This dials back to 50 watts, which is the lowest power setting that's supported by the processor. And we can see for different applications, we get runtime effects at different power caps. So the Lulesh execution happens to be the hottest of the benchmarks that were run. We see effects starting at around 100 watts, and that has a nice parabolic curve shape to it as we continue to dial that back. The AMG MPI run is the next warmest, and we see that also has a parabolic shape to it, but that curve doesn't start until a little further back as we dial that power back on these runs. The cold applications really don't see any effect at all. The CoMD and Mini-FE settings there at the bottom, we can see that those keep approximately the same runtime back to about 55 watts in the power setting. So different power caps affect different applications differently. but we do have some consistent shapes that we can see with respect to the way that the power, or the way that the diminishing power cap changes the runtime if the runtime is changed. Okay, so non-constant power, I think, is one of the things to think about for this. I don't like average power as a way to estimate what power performance is. This is mini-FE run across 8 nodes using the OpenMP configuration and MPI. And we see that it has a high power consumption phase up in the beginning when it's setting up. It has a long, low power consumption phase in the middle, and then it has a high power consumption phase there at the end just before it exits computation. If we went and got an average power figure for mini-FE, we get 50 watts for the average power on the run there on the left, where we effectively don't have a power cap. The power cap is at 115 watts, that yellow line along the top. If we run mini-FE in the same configuration with the 50-watt power cap, we get a new average power figure of 36 watts, and we get an extended runtime on it. So an average power setting does not produce the same runtime as the average power computation, or as what we computed with the average power when we had no power cap. Another thing to notice is that the only time runtime extension or runtime dilation was during what would have been a high power phase during the execution. So if we go and do the math on those annotated times, we can see that the runtime dilation was there during the high power phases at the beginning and at the end, and that the low power phases kept pretty much the same runtime for those windows. Okay, this makes sense when we remember that our computers are machines, right? They're actually physically doing work, and that work involves going and changing those transistor states. Of course, all the energy that we pour into our machine turns to heat in our system. So if I don't have enough power to do all of the work in this time interval, some of that work has to be moved to the next time interval. So again, here we have that high power phase. Because the power cap is beneath the amount of work that has to be done, some of that work gets deferred, and that shows up as this runtime dilation, or some of those transistor state changes that would have happened in the previous second now get pushed into that next second during execution. Okay. So this leads to a simple algorithm to try and do power control without knowing things in advance. That's what PowerSched is going to use. We're going to go and gather what the current consumption and allocation is for each component on the system. Okay, if you were a component that has a big gap between how much power was allocated and how much power is being consumed, you're probably in one of these low power phases. And if I take some of that power back, I won't perturb your runtime. If your consumption is right up against your allocation, you're probably in a high power phase and don't have enough power to run at your fastest speed. So I will try and take some of the power that I reclaimed from a socket, from components that were in their low power phase, and give that to components that are operating in a high power phase. We implemented this using several different communication technologies. We'll be looking mostly at results from the MPI implementation of PowerSched, but we did build it on some other transports. For PowerSched, of course, we are in this hard enforcement space. And how do we go and prove that PowerSched's doing the right thing? For the mechanism, we're going to trust that Intel's chip does what Intel's chip says that it does. So if Intel says we can set a power cap and they'll maintain it, we're going to believe that their hardware actually does that. most of the experimental evidence indicates that they do pretty well at that in their modern chip revisions. So for all sockets at all times, if we have an allocation, the consumption will be beneath that allocation, for less than or equal to that allocation. Okay, for Pauskud's algorithm, we're going to go and work in a couple of phases. So we'll start with an initial state of the system that's safe. And when we turn the machine on, we can just set the power to be evenly distributed across all of the sockets in the system. That's a perfectly safe starting point. Then at each scheduling interval, we'll go and do 3 steps. The first step is to identify what the current power consumption is. That won't change the allocation, so we're still in a safe space algorithmically. In the next step, we will only make down allocations. So if you have a component that has some difference between the allocation and consumption, we'll lower that allocation to be closer to the observed consumption. And we can do that safely. Allocating things up, we have to say a bunch more stuff, and we could go through that formally, or we can look at this visually. All right, so I have a system with power limit L, and I'm going to go and distribute that power limit over the green and yellow jobs in the system. Starting out, we'll go and set the allocations equal for both of those jobs in the system, or for both of those components in the system. Okay, then we do the step where we take the measurement, and the green job is consuming most of its allocation, and the yellow job is consuming significantly less than its allocation. All right, so that's the measurement step. Allocations haven't changed. The system is still in a safe state. For the allocation down, we will remove some of the surplus allocation that the yellow job had and tuck that away in a space for allocation in the next step. Because we've allocated things down, we're still in a safe state. And that S is going to be the difference between the down allocations and the total system power limit. So altogether, the allocations plus that overhead is a safe quantity within the overall system power limit. Then we make the up allocation where we allocate that spare power to the green job, and we're still within our system-wide power cap. Right, so we implemented it and then we ran it. These are results across 10 executions of several benchmarks run concurrently. So we have several different jobs running at the same time for each of these 10 runs. And then we have different power caps. So the static results are the results where we have gone and set the same power cap on all of the components. And the dynamic results are the results when Pauskud is making power decisions every second across the 128 nodes that these jobs were run on. I think it was 16 nodes per job in that setting. And we did really well at 70 watts. Right? We got a 14% improvement with respect to how long it took to complete all of the jobs that were scheduled on the machine. So no single job saw a large improvement, but in aggregate, you see an improvement where the total time to evict all jobs in the queue goes down. So of course, we want to go and understand that a little better. So we have a plot here. Each of the colors represents one of the jobs in the system. We can see that both in terms of the aggregate power used plotted over one another in the top plots. We can also see that in terms of energy there in the bottom set of plots. The ones on the left are the static plots. And you can see that hard straight line where the power cap was reached on the components for the jobs that were high power consumers on the left. With Pauskud, we're able to go and take some of the power allocation on those sockets that are running low-consuming jobs and allocate that to the high-consuming jobs. And we see that on the right, where we have the high-power consumer jobs way up above what that average power per job setting ends up looking like. In the stacked plots below, where we can see the total system energy consumption, we can see that there's less white space between the energy that's used and the limit there for the system, so we're more efficiently utilizing the power that we have with the dynamic power scheduling. So these were great results. Went to run it on 256 nodes in addition to 128 nodes, changed the job makeup that we were running, and generated these results. These ones are not as good. The run times don't change a lot. We can see when we're running dynamic and we're power constrained, we can do a little better. But in some of the other cases, we're not doing as well as we were. And even when we're doing better, we're not doing a lot better. Of course, running these experiments is really costly in machine time, right? Because we're going to go and run these experiments several times, and 256 nodes, right? You're consuming a ton of compute hours to go and generate any single column in this table. So we looked a little more at what was going on with the power consumption in our jobs, and what we think was going wrong, or why our results were different for this case, is that we didn't end up with configurations that had high power consumers over the duration of the executions that we were looking at. Right, we have this long tail problem where 25% of the time there is no power constraint on the machine, and so we wouldn't really expect to see much performance gain from being able to power shift. Of course, things we'd like to go and do to get around this would be to implement our own job scheduler so that we can fill those low power phases better. That then introduces a problem on real hardware with conflicting with the system power scheduler. So to address those problems, we introduced a simulation model. And for the simulation model, we're going to think about our program as some function over some start time to some end time, and it will induce a certain amount of power consumption during that runtime. So if I go and give this program function a time value, it will tell me what the instantaneous power consumption would be for that program if it was running on an uncapped processor, on a processor where it could make the maximum number of transistor state changes for that unit time. So this again is just a plot. We have a step function for power consumption that we're looking at here that models some application that has an intense compute phase followed by some low intensity phase. Right, the processor is also going to be modeled by some function, and over every time step there's going to be a certain amount of instruction work, which is an abstract notion of the amount of transistor state change that processor is able to service at that power setting, or at its maximum power setting versus its idle power. Graphically, we might think of the processor like this. There is some idle power, so when the processor isn't servicing any work for a job, it's going to consume some amount of energy. That's captured by the idle. The vendor is going to have some minimum power setting that you are allowed to make on the processor that it can maintain. That's the A min, so the minimum allocation that could be made. And then we have a notion of a maximum power setting. What's the most power that this chip could draw? And that's going to be the setting for the thermal power dissipation on the processor. So at its highest setting, it will go and complete all of the work that it could complete, and at the idle setting, it will complete none of the work that could be complete for a user application. All right, simulator model then mathematically gets represented this way. We want to normalize there between 0 and 1, which is why we have the ratio under the radical. And the radical is there so that we get that polynomial shape as we dial back the power setting. This model does not tightly match a real processor. That's intentional because I was more interested in what are the general effects on runtime as we have multiple jobs on a large cluster and we change these power settings. I guess the other thing to mention with the program model is, of course, the program can induce a certain amount of work over an interval. And that's what the program formula is about. How much work could this program induce over some interval? And the processor has a certain amount of work that it can service over an interval. And what that's going to mean as we step through the simulation is we will check first to see, for the interval that I'm computing, did the program exceed the power cap? If it did not exceed the power cap, then the program advances at the same rate as the simulation advances. If the program's power consumption would exceed what the processor's power cap is, then we need to compute how much of the work the processor could have done. So we'll solve the program integral and leave that E prime empty. And we'll try and compute what that E prime value needs to be so that the program instruction work done matches the amount of instruction work that the processor could have done over that time interval. And that will dilate the program's runtime, right? Because the program, in that 1 second step that the processor made, will make slightly less than 1 second progress in its own execution. Okay, so graphically, we can think about an execution here where we have a cap at 105 watts. The program could induce 80 watts worth of work. And in this case, the program and the simulation advance the same amount of time. If the processor power cap was lower, like say 60, there is a certain amount of work now that needs to be deferred to a future time step. So that difference between that 60 watt point on the curve and that 80 watt point on the curve then gets deferred into the next simulation time step, and we get a runtime dilation on the program that we're simulating. So for validation, we go and look at when we see runtime dilation in our executions. This step program matches kind of with the mini-FE plot that we were looking at earlier in the presentation, and we see that our runtime is dilated correctly by the simulator with respect to dilating only during the high power consumption phases of our program execution. We might also go and try several different applications in different configurations, and we see the same characteristic shape on our runtime, program runtimes, as we sweep from high power settings to low power settings in our simulation. So we're getting the same characteristic results as we see on real hardware. If it was important to match real hardware, we could go and potentially use a machine learning technique to go and adjust that processor model formula so that it matched our hardware more closely. But for getting a general sense of the way power capping will affect execution, this looks to be generating the right kinds of results. Okay, the simulator is implemented in Python. It scales linearly as we'd expect as we increase the length of the simulation and as we increase the size of the cluster that we work with. And then using the simulator, we can get cleaner results back, right? In real life, our computers are very noisy due to small temporal things that happen as we shoot things over the network. Simulator helps dial back some of that non-determinism, and we can investigate various configurations that might be interesting for our power scheduler. In this slide, we have the best the best case for PowSched. We have several jobs that are running in our system. Each job is represented by a different color. And these jobs have their high and low power consumption arranged in a time-synchronized way such that they could share power with one another. And in the static power scheduling, we can see the allocated but unused power, that light-colored part, as those jobs run. Where with the dynamic power scheduler, we're able to effectively shift that unused power to the high-consuming jobs. And we get to keep our cap, and we get to keep shorter runtime there to run those jobs. Of course, dynamic shifting doesn't always get us better runtime. This is the worst case for PowerSched. Again, we have time-aligned executions, but this time they're time-aligned in a way so that they all change in the same direction and the same amount as we step forward. And in those cases, we can't get any performance gain from PowerSched. So this simulation run helps us to understand in what environments we would expect to get better performance from the dynamic power scheduler. And so your job makeup has an impact on what it means or what kinds of results you're going to see as you run your power scheduling experiments. Then I wanted to go and implement a couple of different scheduling strategies. This result shocked me the first time I ran it because so much of the work is looking at reservation-based strategies. Right? My reservation-based strategy in this case took twice as long to complete as the static strategy did, roughly. And this has to do with the idle power in the cluster, right? Just having the node on means that it's going to draw some amount of energy. All right, and as I'm going and handling this as a resource allocation problem, I have to think both about the resources that I have allocated to active jobs and the resources that I have allocated just by the fact that my machine is of particular size. So there is enough power to go and run the green job along with the red and yellow jobs, but it can't run because there would still be some nodes that didn't have a job running on them. And that idle power would have caused us to exceed the cap. So if we're in a hard enforcement setting, that ends up being a problem. Of course, this is just a couple of jobs without a job scheduler under it. What does it look like in a more varied setting? So I implemented a first come, first serve job scheduler in the simulator and generated results like this, where reservation is still giving me a longer runtime. The next step for this work is probably to implement a backfilling job scheduler and see if that can help resolve some of this discrepancy. The results for this are in my dissertation in tabular form. If you're interested to go and look at what the actual runtime impacts were. But for several different job configurations, we see this ranking where reservation is the slowest, followed by static, followed by dynamic, as we change various parameters and how the jobs request their resources from the system. All right, so in conclusion, right, power scheduling and energy efficiency address different problems. Energy efficiency is going to go and reduce the total energy used to complete a computation. Power scheduling is looking more at this rate problem. So even if I have a highly energy efficient code, if I have a power constraint, right, I may not be able to use it even in that case. Hard enforcement of power caps can be done efficiently without a priori knowledge, right? Lots of work in the power scheduling space. You're going to go and have part of that work devoted to describing how they're modeling the application. You'll note as we talked about the PowerSched algorithm, we didn't know anything about the application or even that applications were on the machine, right? We just had those differences between the power allocation and consumption across the components. And I guess the last conclusion here is that it looks like even that naive dynamic power scheduling strategy generates good results, but I'd like to go and continue to press on that, right? Because there are things we'd like to think we could do better if we had more information. So that is where the future work in this is probably headed. Of course, an acknowledgement. This work wouldn't have been possible without the collaborators that I worked with, Alan Maloney, Tapazia Patke, Martin Schultz, and Barry Roundtree. Of course, the funding acknowledgements. I have for you today. Thank you for your time and attention.